So we'll start with a demonstration of question 23, which is we need to have a job, and we need to submit a job that asks for 4 tasks on 1 node, and we would like not to run on any nodes with any other jobs. Now, this is useful if you're trying to debug this job and problems. It's important to note that you may get charged for all the resources that you actually stop other people from using. So if you run this on a 32-core node, your group will get charged for 32 cores. Now, this will be used in terms of your priority, right? Question 23. Once again, we're going to want to put in the reservation for the workshop. And since I have multiple accounting groups, I need to specify one. And the way we ask to stop other jobs from running is to put in sbatch ---- exclusive. Now, you definitely do not want to do this all the time. This is only for debugging purposes because, as we see here, I'm stopping 28 other cores from being used when I run this. The 4 cores that I'm responsible for, plus the 28 others that are going to be sitting empty because I've asked for this to be exclusive. So once again, we see this job. Notice that I only ask for 4 cores, but it says 1 node and 32 CPUs. Right. Check that again. We're asking for 4 tasks, 1 node, but we're asking for exclusive. We do an S control. Show job name. We can see that we're actually getting charged for 32 cores. But we only ask for 4 cores and for 4 tasks with 1 CPU per task. So this is definitely a waste of resources for running big jobs, but if your jobs keep failing and you can't attribute it to something else, you could try running one and see if potentially it's other people on the same node. So most of the servers, these jobs are isolated. So we've shown C groups, they isolate your jobs from other people that are running on the same server. This is good because it protects you if somebody's using too many resources or has an issue. But the isolation isn't perfect. There is ways other people can affect you when you're running on a node with other people. And this is one way of testing whether your job has issues. I have one more than one. Yeah. It's still running, sorry. Oh yeah, it's going to take about 6 minutes to run. So we could look at it again. So once again, you're going to get charged for a lot more cores than you're using, because that's how many cores this job stops other people from running. So you can ask for 4 cores, ask for exclusive, but you'll get charged for 32. We could look at the next question as well. The output of this question 23, it's just going to say host name as well. So. Question 24, so we have job dependencies. We want to submit a Cedar job named dep1 that has a wall time of 2 minutes, that sleeps for 120 seconds, and then submit Cedar job 22b that waits until job dep2 is done, wall time of 2 minutes, and it has to sleep for 120 seconds. Okay. So in here, just like in all the other ones, I need to put in my account, the reservation that we're using, and my email. Now you can see that these 24.1 and 24.2 are similar jobs. They all ask for 1 task and 1 node, or 2 minutes. The first one is called dep1. The second one we see is called dep2. Now, when we run the first one, if we just did an sbatch, answer q21.show, right? We get submitted job batch and a batch number. But that doesn't create a dependency. take the output of that, write it out, get the job ID number, and then submit the second one with a dependency after correctly running the first job number. And then run the submission with question 24.2.shell. I made that script executable, so we take that output line, we get the job ID, and we submit the second job. And unfortunately, the second job failed because the scheduling system didn't quite run correctly. Okay, let's do that again. Sometimes your SBatch fails, or your SQ fails because the scheduling system is quite busy. There we go. So we see the first job, which was submitted. We got its job ID, and we submitted the second job. And we want to do an scontrol show job. And we see here that the job is pending. The reason there's a dependency, and it's waiting until the first job here runs. And once again, we still have the dependency. No, we run it twice. We actually did get the second dependency through. The first time around as well. So we see that the first the first part of the job 20, the job for the answer 24 is running, and the second part is going to start soon. We see here the job that ends with 901. The dependency one is finished. And then here we see the dependency 2 starting after the first one has finished. So this is the way you can break apart a larger job. It will be submitted and ready to run the moment the first one finishes. So if you need to have a very long run, say you need to run for months, but you could break it up into pieces, well, this is the way you would do it. You could make each of these small. So you can have each of these run for 72 hours and have the next one start off immediately, one after the other. So this is a very useful feature for people that would like to break apart their jobs into smaller pieces, but would like to have them start immediately one after the other without having to manually submit another job when your first one finishes. In here, we didn't have to do anything. We just had to wait until the first one finishes, and then the second one's available. So, is there any questions? Question 25 was removed, so we'll move on to question 26. So submit a job that runs in a temporary directory, use no more than 1 GB of space. Okay. So the way you would do that is you have a minus temp equals 1G. That's what requires the space. Reserve the space. it's running. And through S-control show job, we can see that this job is running. We can see that unlike the last time, this one has no dependency. And somewhere in here, we should probably see the requested storage as well. Oh, there we go. Minimum temp disk node 1 gigabyte. So that means that this job requires a minimum of 1 gigabyte of space in the temporary disk storage. So this temporary storage for running things like Gaussian jobs, those directories go away. So if you were to use this, you would have to copy the data. If you wrote any output there and you wanted to keep it, if it wasn't just a temporary cache, you would have to copy the data back to the directory that we are in before your job finishes, because this directory is going to go away when the job does. If you're interested to see how this would work, you could also do this interactively and look at the directory. So running stuff interactively is a good way of understanding what's going on inside the scheduling system.
Sorry, one question.
Yeah.
How much temporary storage is available?
This depends on the cluster. So I think there's more on Cedar than there is in Graham. You would have to look at the Cedar specifications.
Okay, will that be part of our own space, or this on top of whatever we have?
So this is, your space is on a shared file system, right?
Mm-hmm.
So when we look back at one of the first slides here in our talk, and we look at the cluster, your space, so Scratch and Project, those are Lustre file systems. So they sit on specialized nodes here. And they are accessible via this high-speed InfiniBand or OmniPath network. These are really high-performance, extremely fast, low-latency networks that are used for running clusters. The storage, the file system sits there, right? So it doesn't matter if you're on Cedar 1 or Cedar 256. You can still see the same project file system, right? It's sort of like NFS, but much, much faster, right? And in the Windows world, it would be like, you know, a Samba share. So where you have multiple Windows machine or multiple Linux machines seeing the same file system, right? So that's the file system that Project and Scratch is in. The temporary storage is little disks attached to the compute nodes themselves. So they are, each of these compute nodes can have a disk, and you can't access the disk from one compute node when you're sitting on another. And not only that, this data gets deleted automatically when your job finishes. So these compute nodes, their only purpose is to run jobs. So there is a local disk that you could read and write to that you could use for this. Local disks are much faster for small files. So if you have Gaussian, which requires a very, very large number of small files, and it needs to access them there and back all the time, the raster file system, just like you would have in NFS or Samba with Windows or whatever shared file system you're using, does not like to do many small files. It will be very, very slow. But a local disk for small files is much, much faster. So you could use this, write your temporary files without affecting the performance of the file system of other people using the file system across the cluster, and also that you're not slow, that your job won't be slowed by the slower file system that is shared. Now, that file system is actually quite fast if you're doing long reads of large files, but it does not like small files. Any shared file system do not like small files. So this is an advantage for you to use, and it's an advantage that you're not slowing down everybody on the rest of the cluster that is using the shared file system. Did I answer your question effectively?
Yes, thank you.
Okay. So question 27 is to submit a Cedar job that prints the partitions that it was running on. Okay, we can do that. Once again, we may have to edit this to put in the fact that we want to run inside the reservation. In my accounting group. And basically, in here, we're echoing the Slurm job partition variable. And we could also print out all the other Slurm variables. We see the job run. Oh, did I start the wrong one? Yeah, number 27. Okay, our job was run. So in this case, we see that the partition we run in was CPU-based by core B1, which is correct because if we look back at the partitions that we were running in, we're running in CPU-based because we're not asking for a huge amount of memory. We are asking for a few cores, so we're in the by-core partition. And we're running in a V1 because we're asking for a short wall time. So V1 is less than 3 hours of wall time. Now, once again, I'd like to emphasize this. So if you could make your job shorter, they are much more likely to run quicker because they could fill in all the gaps in the scheduling system. Also, if you're trying to run a larger job, you should use a whole node because then your job can run anywhere as opposed to just in the by-core partition. So probably the best type of job you could run would be, or the easiest one to schedule would be a 3-hour-long job that uses a whole node. Those are really, really easy to run, and they fill in the scheduling, the holes in the scheduling system quite nicely. Because there's other people that are trying to run really large, many-node jobs. And while those resources are being gathered, a 3-hour-long job could start and run in one of those nodes. And as well, we could see all the other Slurm environment variables. You know, which nodes we're running on. How much memory. We didn't ask for memory, so we got a very small amount. You know, how many tasks we're running, which is 1, because that's the default, and so on. Okay, number 28. So this is an exercise which is only available to users which have rack accounting groups, and so on. So you could do we could do an S account manager list users, or an SS share. And we could see all the multiple different accounting groups. I think also SS share, I think minus L. But there's many different flags you could put to all these commands. You can see I have a whole bunch of different accounting groups. So one of those accounting groups, for instance, I have is complete kind of a debug accounting group for administrators that are trying to debug programs. You won't have that, but you may have an allocation. So if you have a rack allocation and you want to specify that to run your job inside your group's rack allocation, you would have to specify it this way. I also I'm actually part of 2 different groups, the default Camille group and the default Camille AB group. So I can actually edit question 28. Also, when I try to run without specifying an accounting group, we have an error because I'm part of multiple accounting groups, so I could actually pick anyone. And I'm going to pick Def Camille. So in this example, I change it to the other default accounting group I'm part of, and it's running. So it's quite possible that you can be part of two default accounting groups. This happens when you're part of two research groups. You could be part of two professors' projects, and you should be running the jobs in the correct group, right? So if you're part of two research projects, you should be running the jobs for one research project that you're doing for one professor, and doing the same thing for the other group, for the other professor. People may be upset with you if you're using their allocation for the wrong, the other group's computation, right? Okay. Okay, so we're going to go through here and look at some of the getting information on your job. So SQ minus U, that lists all current jobs from a user. If you add a minus T to there, that will list pending jobs. SQ minus U minus T running will give you running. You may also want to do an SQ minus L. It gives you more information. It actually prints out pending instead of having PD. SQ minus P, partition name, will list all the jobs in the partition. S control, show job, gives you lots of information about the job. Minus D gives you a lot more detailed information. You can also format stuff. So SQ allows you to do job formatting, provided you copy the command correctly. You may not want to have a space between there. Oh, and also Microsoft PowerPoint capitalizes your words. So you could get a lot more information by what's it called, changing the output. If you do man SQ, you'll get the output formatting. SS stat, as we see, you could do an SS stat format, and it'll list the resources used by your completed job. So average CPU time, max memory, max virtual memory, and so on. You could do an S account minus U username, and you could list resources used by all the jobs of a single user. S prio gives you information on priority. SQ. And we could read this SQ here. The font is a bit larger here. You can see the job ID. In this case, I believe this has a job ID and array ID. Partition name, my job name, my username, its state. In this case, it's running. Time it has left, I believe. The number of nodes, and the node list. This reason here is either the node list of all the nodes it's running, or the reason that it's not running right now. And reasons can be such as it doesn't have a high enough priority, or there's not enough empty resources, that sort of thing. If you do on a minus U username, it just does that for yourself. And here we have a few reasons. One of these could be dependency. So it's not starting because it's dependent on some other job. You can have a dependency never satisfied. That means that this job was waiting for another job to finish correctly, and it potentially hasn't finished correctly. Maybe it crashed, and your second job can't start because the first one errored out. So there's the reason. So if we just look at minus T pending, for all my pending jobs here, they're not starting because there's not enough resources. Priority, my job doesn't have enough priority to start. Maybe there are enough resources for this one to start, but some other job was started instead. And dependency never satisfied. So once again, in this case, this job will never run because a job that it was dependent upon may have failed. When we see the same thing with minus T running, we could see a list of node names here. So in this case, this is node Xeno1. Sometimes these nodes come out with Cedar 72, 88, 92, and 95. And sometimes there's ranges, like 81 to 83 plus 98. So these are the nodes that this job is running on. We could also list jobs by partition. So we could be only looking at jobs in CPU base, for instance. And then we can actually do an SQ query. So let's say we wanted to see all the partitions that a job can be in. So as we said earlier about partitions, your job can be in multiple partitions. It usually is. So usually it has a main partition like CPU base by port v1. But we often also have a CPU backfill partition. So that's in that partition, your job would have lower priority, and it's used to we use this sometimes to run. So those nodes that are reserved for whole nodes or for long-running jobs, we can backfill them with shorter jobs, and we will. And by backfill means that we'll allow short Cedar jobs to run in that area. There's also priority information here. So we have an S-control show job. Here we have some of it colored. We see my user ID, some priority, the fact that this job is completed. Its runtime, its maximum wall time or time limit. There's when it started, how long did it sit in the queue, when it ended, node list, how many resources it used, and how many resources I'm going to get charged for. and all kinds of other information. So S-Prio shows your job's priority. The higher the better. So jobs, yeah, we'll talk about jobs priority and where it comes from a bit later. So we've seen most of these. We'll do an S-Prio minus N. I think it's the one we haven't seen. So we could see the job, the priority from sitting in a very long time in the queue, priority from fair share, priority from partition if there is any, and how many resources the job uses. Are there any questions? So if there's, okay, so this is I'll do a demo of how to change the output. So the SQ minus O, it allows you to make your own output formatting. And let's say you don't want one of these pieces of information. Let's say I don't think you need, I think this is the time. Yeah, so you could remove it and it's a bit more compact, or you could add features here. If you do a man SQ, you could see all the options, including the output formatting. You could do -L for long, or you could go in, look at the output formatting, and get exactly what information you want. There's lots and lots of options, including exactly how you want the time displayed and so on. Are there any questions?
I have two kind of general questions. So the first one is on dependency. Let's say you submit a job and it's dependent on another one finishing correctly, and the first job fails. Do I need to resubmit the second job, or will it run the moment the first one ends correctly?
It will do what you tell it to do. So you could set the dependency to just be after. So it'll do, the second one will run just after, right?
Independently on whether the first ones ended correctly or not?
Exactly. If you want to wait until it acts correct, edits after it's correct, you do an after OK. So the second one will only run after the first one has finished and has run successfully.
Okay, so let's say the first one fails and I resubmit the first one, and eventually it runs okay. Do I need to resubmit the other one because now I have a different job ID?
Yes.
Okay.
You would either have to edit that job, which would be fairly involved, or you would need to submit a second one that depends upon the. So because the job depends on the job ID, right? So if you submitted your original script again, That second one has a different job ID. So you would either have to change the dependency on the following job, or you would have to kill that following job, submit a replacement following job with the correct dependency set.
Okay, yeah, that makes sense. And then the other question is about memory. Let's say you submit a job using only one core.
Mm-hmm.
Assuming that there cannot be more than one job running on the same core, will it be the same for me to ask for 128 gigabytes or anything less than that?
Okay,
Since
so
I'm using the whole core.
a core is just a processor, right? So these servers have 32 processors, right?
Yeah.
There are actually 2 chips. Each of these servers, each of these nodes have 2 chips with 16 cores each, for a total of 32. So if you ask for a single core, then, and you don't ask for exclusive, then the other 31 cores on that node could be run by other people's jobs, right?
Okay.
So the base nodes, if we look back at the over here, so Cedar, for instance, has a whole bunch of different types of nodes. But the basic ones have 4 gigabytes per core, or 4 times 32 gigabytes, right? So it's 128 gigabytes in total. Now, some of that's used by the operating system, as we mentioned earlier, but not very much. So they basically have 128 gigabytes available for your job to run, slightly less. That's the base. So if you run only one core and ask for say 1 gigabyte, then all the remaining memory could be used by the other jobs. Unless you ask for exclusive, right?
Okay.
Now, if you ask for 32 cores, then on a node, then nobody else can use the memory, right? If you use all the cores, then there is, like, cores and memory come on a server together. If you use all the cores, then nobody else can use any of the remaining memory. There's different types of nodes. So there's the 4 gig per core, the 8 gig per core, 16 gig per core, 48 gig per core, and 96 gig per core nodes on Cedar. And there's a lot less of the 96 gigabytes per core nodes than there is for the 4 gig per core, right? There's only 4 of those super high memory nodes, as opposed to 576 of the basic ones. Did that answer your question? And are there any other questions?
Yeah, thanks.
Okay. Does anybody else have any other questions? Okay. So now we're going to talk about priority, allocations and fair share, cluster limits, reservations and topology, getting information on the cluster, and troubleshooting your jobs. So priority can only be positive in Slurm, and only the relative priority matters. So if one job has higher priority than another, it doesn't matter if one job has priority of 1 million and the other one has a priority of 1,000,001. Or if that scenario, the scheduling system acts the same as if one job had priority of 1 million and the other one has a priority of 1. It's only the ordering of the jobs that matters. Also, as we saw earlier, the highest priority job may not run first. So a job that uses a small amount of resources that are in great supply may easily run before a high priority job that's requesting scarce resources or resources that are being used currently by running jobs. And in Compute Canada, priority is determined per group via fair share and how long your job sits in a queue. So it's determined upon how much your group has used recently compared to their allocation. That's the fair share bit. And you get extra priority for your job sitting in the queue. And that means that eventually all jobs should run. If we didn't have this, potentially certain groups may, or certain people may not be able to run jobs. So you do get priority for sitting in the queue, but not very much. Mostly it's based upon how much your group has used compared to its allocation, which we'll talk about a bit later. And it's the priority that matters. And if we look at Esprio, we actually see that priority comes from different places for how long the job is, from its age, and from its fair share, potentially from its partition. But as we see, it's the fair share that's really important. Age, not so much. The other thing with Esprio you could actually see is the resources that are being actually tracked. How much resources does this job use? So what is fair share? Fair share is the mechanism that allows historical resource utilization information to be incorporated into job feasibility and priority decisions. So in Slurm, priority ranges from 0 to 1. In Compute Canada, fair share compares your group's target usage to your group's actual usage during a time period. If your group has used less than your group's share, you're given higher priority. And if your group has used more than its share, you're giving lower priority. This way, the scheduling system tries to make sure that every group gets their share. An important part about fair share is that fair share decays. So fair share is a weighted average. A weighted average is used so that your recent usage is more important than the usage at the end of the time period. The time period for Cedar and Graham are 30 days, I believe. But your usage today and yesterday is a lot more important than your usage 30 days ago. And also your non-usage, right? Both your usage and your non-usage. And this is done to stop the schedule, your priorities from fluctuating wildly and to be more fair. So fair share treat CPU and GPU and their equivalents. So we use CPU and GPU equivalent resources in all our calculations. So if your job uses all the memory, disk, or any other resource on a node, and half the CPUs, the scheduling system will charge or use in its calculations as if you used all the CPUs on that node. So we basically care about what fraction of the system did your job take. If it requires all the memory but only one core, the scheduling system will treat it as if you took the whole node, all the cores, or all the memory. It's basically the share of the node or server that your job used, or stopped other people from using, as we saw. In our case, there's also separate accounting groups for CPUs and GPUs. So Compute Canada allocates CPUs and GPUs separately. So the GPU portion of their jobs are calculated separately from the CPU portions. And you have different accounting groups. So if you actually showed and run you can actually see that there is a default Camille AB underscore CPU, and a default Camel AD GPU. So you have two accounting groups. Now, you don't actually have to put in the underscore CPU and underscore GPU. There's a QSub wrapper script. There is a job submission plugin script that actually does this for you automatically and puts the appropriate ending upon the partitioning. So for GPU jobs, we only count the number of GPUs used or the equivalent in terms of other resources. So is there any questions about this? Okay. So we also have something called a fair share tree. So it's possible that for a project leader to divide the target allocation of resources in a group. So your priority is determined upon the combination of your group's usage compared to your group's target usage, as well as your subgroup's usage compared to the subgroup's target usage as well as your individual usage compared to your individual target. But the priority of anyone's job will be primarily influenced by the top of the tree rather than the subgroups or the individual usage. But this is one way a PI can distribute allocations within a group. So let's look at some fair share tree basics. So here's an example of a fair share tree. Fair share trees shares are different than the fair share tree shares are different shares on the different levels. So the fair share tree shares don't mean anything other than the meaning we give them. If they add up to 100%, it's percentage. If they add up to the number of cores, then each share is expressed in cores. And in Slurm, all these shares have to be integers. The usage in a group is includes the usage of its subgroups, and normalized share are the fraction of the system that the user receives. So here we see that group 1, its normalized share is 50% because it has a share of 2, but at that level there's actually 4 shares. So it's 2 of 4, or 50%. We see subgroup 1 has 4 shares, but subgroup 2 has 1 share, and they're both part of group 2. So the normalized share of subgroup 1 is 4 shares of 4 plus 1, or 4/5. But that's 4/5 of group's 1 share. So 4/5 of 1/2 is 40%. So this is the current fair share tree. Basically, we have set up all the rack users to sit off the root, and then have all the default users share in the same pool of resources, which was the total number of CPUs that weren't allocated, or the total number of GPUs that weren't allocated, that they were evenly divided by all the default groups. We're actually changing this. So what happened here is that there's a slight issue with this fair share tree that we have set up currently. Basically, what it meant is that all the groups all the default groups were all in the same pool here, and they were all sharing a number of cores. What happened is, so they were sharing all the unallocated cores, but some users which understood this scheduling system were running short jobs that could fit between the rack allocated groups. And they basically used up all the resources that were available to all the default users. So it's difficult for default users to run jobs. Then new fair share tree basically is going to divide up the share that was set up for all default users evenly into each group. So basically, what we're going to have is each research group with a default account is going to get the total amount of non-allocated cores divided by the number of default research groups. That's going to be their share. And there's some fancy math that you need because the system doesn't allow you to have fractional shares. So it can't give you 1.5 cores as a share when we have to multiply all these share numbers by the number of non-allocated projects, number of default projects, basically. Yeah. Any questions on this? So this change is coming up, and we're going to do it in the next month on both Cedar and Graham. And this should help with the default account users getting to run more. The actual tree is actually going to look more like this, where they're all coming out of the same root, but both the GPUs and the CPUs and the default accounts and the fact that there's But this is just for CPUs, a simplified diagram. Any questions? Yeah. So this fair share tree is basically multi-level fairness, where you have both fairness between groups and subgroups and individuals. When you look at the system, you will see something called effective usage. Now, this is no longer used by Compute Canada, but it is shown when you run some of these commands. So you could have your group could have no usage of the system, but it could have effective usage. Or you as a personally could have no usage of the system, but you could have an effective usage. What this is, and you should ignore it, but what this is not a bug. The mechanism by which Compute Canada, or by which Slurm, used to take into account the fact that your group, like you individually may not have used any resources, but your group may have used more than its share. So in order to take that into account, basically, the concept of effective usage was created, and the system pretended that you had some usage based upon the usage of other people in your group. And then it used that effective usage to calculate your priority. It includes your usage, but also your group's usage and your subgroup's usage and your supergroup's usage at every single level. So this is sometimes deceptive to people, but you could effectively ignore this. Also, we've moved on in the last month to a fair share tree priority algorithm. So the algorithm has changed a little bit. Basically, it works by calculating the level fair share at each level of the fair share tree. It calculates the group or the user share versus their use, divided by their use. And it orders all accounts, all accounting groups, all groups, and users in each level. It then orders all the users and actually gives a priority in terms of the ordering. So if there are 3 users and one has used more than their share, or even if all have used more well, if there's 3 users and one has used more than his share, the second one is in the middle and the third one has used much less, it's going to be always give the highest priority user, what's it called, a priority of 1, the second highest priority user a priority of 0.67, and the third user is going to get a priority of 0.3. So it just does it by ordering. The system figures out which group has used less and just orders them properly. But this doesn't matter because the priority, the way the jobs are run, it's in order of priority anyway, right? When we look back at the way that the jobs are run, we order in terms of priority. We don't care if the priority of this job 1 was only slightly higher than priority of job 2 or not. That doesn't matter, right? Because our actions are to run the highest priority job first, run the second highest priority job second. Yeah. And your job's priority is the sum of all the weighted sums of all the factors that have been enabled. So it's the priority weight H by the H factor, the priority weight fair share. So basically, how important do we think that your job sitting in a queue is, times the length of time it's sat in a queue, plus how much priority we give to fair share. So this allows us to give greater priority to jobs that have been waiting in a queue for a long time, and to determine how important that is relative to the priority from fair share. And without an H factor, a larger job by user with a small allocation may never run. So is there any questions about priority and shares and fair share trees? Any question at all? Okay. You could get your group's usage status by SS share. And there's information here. There's raw shares, but there's also normalized share, which is like I think the fraction of the cluster. There's raw usage and normalized usage. So how much your usage actually has been. Effective usage, which was that imputed value that we never use. And the fair share that comes from that. And the SS share minus L gives you the level fair share as well. As you can see here, there was infinity. That is because the usage is 0. So if you have a share, but you haven't used anything, then your level fair share priority will be very high, infinitely high, which makes sense. If your group hasn't run any jobs, and they do have a share, they should get some of them. So you have a S pre-O minus N, and it shows you the priority, and from the different parts as well. Okay, so let's go through multiple allocations and accounting groups. So this occurs when a group gets a RAC. A resource allocation committee for competition allocation, and therefore a new allocation that becomes the default allocation for that group. It occurs when the user is part of multiple Compute Canada groups. One can select default allocation. Yeah. Ignore that sentence. That's actually the WestGrid one for the WestGrid clusters. In order to specify an accounting group to charge and to figure out the priority, use the following example in the submission script. You basically set the SBatch minus account and then accounting group name. That's how you do it. You've seen me do this every single time I've been running one of these jobs. Okay, what does an allocation mean? Well, what it means is that if you request average resources continuously throughout the time period and run jobs, you are guaranteed to get at least your allocated resources over the time period. So that means that if you got a Compute Canada rack allocation and you continuously run normal sized jobs and you have jobs in the queue all the time, you're guaranteed mathematically to get your resources. What if you don't have applied for an allocation? Well, you have a default allocation. Now, some people don't like this definition of allocation. They think that if you were promised 100 core years, that's 100 cores times a year of time. You should be able to use it anytime you want. But think about it this way. It's impossible for allocation to be defined as anytime you ask. The resources are allocated and you will receive them. So if two users are given 50% of a cluster each, and both don't start running jobs until the 6th month, halfway through the allocation period, they both cannot get 100% of the cluster for the remaining 6 months. Right? There's only one cluster. And if one of the users, if one of the users had run and used the whole cluster for the first 6 months, and the other one had run and used the whole cluster for the next 6 months, then they both would have each used 50% of the cluster for the year. But because people tend to procrastinate, and if they both tried to do that in the last 6 months, they couldn't do it. So that's why we have to use that definition of allocations. Also, unless there's an extraordinary situation exists, allocations do not mean that the specified resources are available and sitting idle. So if you're not using those resources, right, then other people could do science. Funding agencies don't like to see resources sitting idle. Now, there's counterexamples, right? And I think the only one I've seen would be extraordinary situation of a tsunami warning center. So in that case, if they need to calculate the waves, if there's an earthquake and they need to calculate, they have sensors, they need to know which beaches are going to be flooded with how high of a tidal wave, and where should the police and fire and other emergency responders go and start evacuating people. Well, in that case, such a center may have resources sitting idle, which is just waiting for an earthquake to occur and for it to run the computation and figure out which beaches and where people could save lives. But unless you're doing something like that, I've never seen large compute resources sitting idle. So allocations, Compute Canada. It's the Compute Canada Resource Allocation Competition. There's a committee there. And of researchers that evaluate proposed allocations on the basis of scientific merits and the resources available. So the way it works is that there is right now a competition that is open right now, and I think roughly for the next month. And the way it works is that you would fill it out. it will be evaluated by technical people first to make sure that you can actually run, that Compute Canada can meet your technical requirements, that the technical requirements specified correctly, and so on. So there's a technical evaluation that reports its finding and recommendations to the bigger committee. There's also a scientific evaluation that's done by a committee of your peers that evaluate give a scientific score on the scientific merits of your proposal. And then both the technical and the scientific, well, it's based upon, your allocation is based upon how many resources are available and your scientific score. The technical evaluation just makes sure that everything's correct. Allocations are done yearly, and there's a RAC call for proposal every September. You can see more information on the WestGrid support account, resource allocation webpage, also the Compute Canada webpage. Any questions about allocations in RAC? So you definitely do want to, if you're not getting enough resources, having issues with that, you definitely want to put in a proposal. And now is the time to talk with your site, your support people in WestGrid to help you create a proposal. So oftentimes it's the same people that do technical evaluations are also available for consult for writing your proposals. So to get more information for you and your group, you just do an S account manager list users. That will list your users and your accounting group. With association shows all the accounting groups. SS share shows your usage info and usage and priority. SS share minus A shows even more information for user and priority. So we could go through that. So if you're doing SQ-U, you won't see anything because there's nothing running, but let's start something, I don't know. Answer 5. You could do an S control show job. The minus DD shows you a lot more information, just like we had with the S control show job by itself. You can see that this job is running. It's been running for 25 seconds. But we have all kinds of other information, including the job submission script. So all the stuff that we set up, the job submission script, as well as where we're writing out the output or the error component of the output, what command we run to submit this job, and so on. So this is used often by the analysts for WestGrid Compute Canada to help support your job. JP minus B. Oh, never mind. Show Q with MOAP again. We could look at S Prio. And we actually see all the priority of all the jobs, and by job ID. We could also do things like sinfo minus minus states equals idle to get us information on how many nodes there are in the cluster. Actually, right. I think, yeah, I think we've gone through this here already. We should continue on. So there's a couple of other things that are going on in the cluster. So there's usage limits. So sometimes your job isn't running and you're trying to figure out why. There's a few other potential reasons. So there's usage limits that prevent the scheduling system from being overloaded. So we don't allow submission of 1 million jobs because the scheduling server will melt. There's also usage limits that prevent a user from monopolizing a cluster. So there's some limits that, if you try to run, if the cluster has crashed and you're the first one on, we will try to stop you from taking over the whole cluster using, the maximum wall time for all the nodes, because then it will take a very long time for the person that logged in half an hour later to run. So there are some limits there. You could get away with having shorter jobs for the whole cluster, like really, really short jobs for the whole cluster. Yeah, we'll let that happen. There's also reservations. So for instance, if somebody's running a workshop, like a scheduling workshop where we are in, a certain amount of nodes can be reserved, and to stop other jobs from running on them, so that only jobs inside the reservation can run. Another reason for reservations would be if the system administrator needed to work on a cluster. Say they need to fix something with node 2 and 3. They would put in a reservation to stop new jobs from starting. So it'd be a system reservation. And then wait until all the... So in this reservation, shorter jobs could still run right before the reservation, right? In this example, node 2, there's still a day until the next reservation. So a job that uses 12 or 24 hours could run. But it stopped any job that would be running past 24 hours from starting. So this is how we created the reservation for you to be able to test and run jobs. Yeah, so there's use for many purposes. For instance, there's a security patch that requires a reboot. We need to run it. Or we have a reservation for a workshop. Yeah, and you can see reservations by scontrol show reservations command. So this tells you something that's going on in the cluster. Here we go. And you can actually see a reservation workshop. And we can actually see all the users that are in this workshop. They're the only ones that can run. And we can see that, there's 8 nodes that this reservation is reserved for us. So once again, if you have short zero jobs, they could fit in before the reservation. Another part is topology. So as more and more devices are added to a system, the ability to have high bandwidth, low latency communication between every device to every other device becomes at first impossible, and then first expensive, then impossible. So this is true between cores on a chip, memory on a machine, chips on a board, GPUs, as well as nodes in a cluster. So the workaround is topology. So only a certain set of resources are connected together with high bandwidth, low latency, non-blocking connections. But connection to other resources are of lower bandwidth, higher latency, larger blocking factor. The result is that jobs running on certain sets of resources are faster than jobs running on certain other sets of resources. And the scheduling system needs to take this into account. So will be a much bigger problem in the future. So this is an example of topology of an older cluster. We had maybe 2 big switches for InfiniBand, and a not where we had good connections with nodes that are connected to switch 1, and good connections with all the nodes connected to switch 2. But if you try to run a job across them, there wasn't quite enough resources. So this is actually an old Jasper cluster image. So Cedar is also like that. Basically, there's 32 nodes attached to a single switch, but so within this switch, all the nodes could communicate at full bandwidth. But if you want to talk to the nodes in some of the other leaf switches, well, they have to talk via the big switch here, and there's not enough bandwidth for all the nodes to communicate to all the other nodes in the switches at full speed. But this blocking factor isn't bad; it's 2 to 1. So you only get half the bandwidth half the total bandwidth if you talk to the other switches. Graham has a much worse. It has an 8 to 1 ratio. So if you're running a job using a whole bunch of nodes, it's much better to sit with it in Graham to be on the same switch. And this is because of its interconnect. So here's a description of all the network connections for Graham. You don't have to know this. This is just a consequence of this. It could be worse. So in WestGrid, we had a system called Hunger-Bee. Its topology was absolutely crazy. And it had all kinds of weird implications. But that system has been decommissioned a few weeks ago. So getting information in your cluster, you can do sinfo -r. You could actually show nodes, how many nodes are available, and if there's a reason why they're down. You could show sinfo -states equals idle, which will show you how many idle nodes there are. And you can look at the partition stats. Once again, the partition stats is a great way of seeing how many partitions are available, how many nodes are available in each partition, how many jobs are trying to run in those nodes, and so on. So we've already talked about partition stats. Okay. Partition stats actually does a few queries, so it can take a few seconds. Oh, the scheduling system is timing out. And so we could see all these partitions here. We could see the different types of nodes, how many jobs are queued, how many are in the by node and in the by core. I would like to have a 5-minute break right now. So if you would like to go through, I would suggest you try to run some of these job examples that we have in that I showed as an example. And please have any questions ready. If you need to take a break, we'll do a 5-minute break right now. So is there any questions? Okay. We could continue on now. So getting information on your cluster. So once again, sinfo states equals idle will show you idle nodes. -R will show you down drained draining nodes and the reason. So potentially in a cluster, in a big cluster, there's always some nodes that are failed. You know, when you have many thousands, tens of thousands, maybe hundreds of thousands of sticks around, you know, computer components fail. And when you have thousands or tens or hundreds of thousands of components, some fail, and they're always getting fixed. You can also show reservation information with scontrol, show reservations. Partition stats is a script to show jobs and nodes by partition. Oh, and S-control actually creates reservations, but you don't have the ability to do that unless you're administrating a cluster. Yeah. So we could do an sinfo minus R. And we could see. Stuff about different states on cluster nodes, including, say, bad DIMs. So, as you can see, these clusters, they operate. There are components that fail all the time. You can do sinfo states equals idle to find out how many idle nodes there are. Now, some nodes are going to be idle, like the ones in our workshop. We're not using them all. Or those ones reserved for interactive jobs and so on. Or a really big job starting. Some of them are going to be idle because enough resources are needed to gather for a bigger job to start. Okay. So why does my job not run? Well, I'm going to list the main reasons. You're trying to run a job. The most often there's usually a problem with the job. Right? Another reason is that the job is blocked now, maybe because there's a dependency or something like that. Other jobs have greater priority. That's very usual too. The resources are not available. So you could be asking for a large amount of resources that are either difficult to gather or impossible, right? If you ask for 4 terabytes of RAM, there is no node on the system that will run. And then there could be also potential with the scheduling system or the cluster itself as a problem. Like there's an outage, or there's a problem with the scheduling system. But those are not likely. The likeliest reason is there's a problem with the job or somebody else has greater priority. So jobs can request more resources than are available on a system or a node or are practical to run. So you could request to run 10,000 cores on Cedar. That would take almost forever to gather them, because that would be a significant fraction of Cedar. You'd have to wait until all the jobs finish. If you request more than 3 terabytes of RAM per node, well, there is no nodes with that much RAM. Or you could request 5 nodes with 2 terabytes each. Now, I think there's only 3 terabyte nodes, or it could be 4. Look back at the table. Where's our table here? Of nodes for Cedar. Yeah, there's 4. So there's 4 3 terabyte nodes. And all those other nodes are using even less resources, have 1.5 terabytes. So if you ask for a whole bunch of nodes with a lot more RAM, a lot of RAM, your job won't run. Now, okay. Problem with my job: do an SQ minus U username, do a S-control show job ID minus D. Is a job on hold? Are there dependencies? What is next thing you should check is your job's priority. Do as prio, compare it to other people's job priority. If you have much lower priority, we'll find out why. Do an SS share. You could do a number of things. You could wait until priority improves over time. You could ask your fellow group members to run less. You could ask your professor, or if you are a PI, you could apply for a rack allocation. So if there's a problem with the cluster, well, you should check if there are resources available. So if you have high priority and your job is queued, check to see if the resources are available, right? Use partition stats to see if there are enough resources available on enough resources to start your job. So even if you have a high priority job, you're not going to be killing jobs that are running already. So check how much resources are available to start your job. Is there a problem with the cluster? So sometimes there's a reservation or system outage. Check the compute calendar webpage, the message of the day on the system to see if there's an outage scheduled. You could check for reservation on the system with a S-control show reservation. That'll show you a reservation. So your job could be fine, but the system may need a security update or a different type of upgrade, or may have lost power, right? So check that the system is fine. And finally, send email to support@computecanada.ca. Right, this is to support if you're having an issue, but please do the following. Make sure you always include at the beginning the name of the cluster, the job ID, and your user ID. So something is wrong somewhere, we don't know where, right? We don't know who you are, what email you sent it from, right? If you send an email, you don't have a user ID, we may, well, if somebody were to answer your question, we would have to figure out who you are in Compute Canada. Like, we'd have to be detectives, and then figure out which cluster you're running on, and then figure out any job IDs. So that might take a long time for somebody to answer your question if you don't include basic things like which cluster you're having an issue with, what's your job ID, what's your user ID. Other things that you can do to improve this is to give the location of the job script you submitted, any output or error of the job run, right? And the best is if you could include the name of the cluster in the subject, right? Like job 1, 2, 3, 4, 5, 6 fails to run on Cedar cluster. Then we write in the subject, so people immediately can see, that's a Cedar problem. The Cedar people will be much more likely to pick it up quickly. Please include a brief but complete description of the problem. You should include any output of any commands like those you described that were described in our talk earlier. Please include any output of commands that you have run which convince you that there is a problem. A lot of these commands give the state of the job or the cluster at the moment that you run them. And if you include them with your email, we can analyze the situation as you saw it. Because if you're having an issue with the scheduling system, potentially say it's caused by cluster outage or something like that. You send an email, somebody else reads it 4 hours later, they look at the cluster and say, everything's fine. I don't know why, I don't see anything wrong, right? But if you have an output, it's much, much easier to track down what the problem is. So, scheduling in the future. Well, we're going to end up with more levels of topology. There's going to be issues with enforcing exclusivity with granularity. So we have C groups, make it even more so that jobs can't affect each other. We may also have to schedule data movements, backups, recovery, latency, bandwidth. Maybe move the job to the data, not the data to the job. There's also things about failure-tolerant jobs and scheduling, power-aware jobs and scheduling. So there's some schedulers out there that actually schedule how much power the cluster uses. So some places, I've read like the Pentagon, that they actually have a limited number of power that they can bring into that building. And they have compute clusters there. And they actually schedule how much, so when a cluster works hard, it uses more power. And components can be powered down when they're not in use. sometimes they have more hardware than they have actual power available, and they actually have to schedule which components run. We could also think about scheduling provisioning of nodes, the scheduling of virtual machines in the cloud and containers, as well as cloud grid scheduling to include both batch jobs and services on the same system, virtual network management, and integrating everything into one big whole. So that's the future.